some 130 million years ago. In a galaxy far away, the smoldering cores of two collapsed stars smashed into each other. The resulting explosion sent a burst of gamma rays streaming through space and rippled the very fabric of the universe. On August 17, those signals reached Earth, and sparked an astronomy revolution. The distant collision created a kilonova, an astronomical marvel that scientists have never seen before. It was the first cosmic event in history to be witnessed via both traditional telescopes, which can observe electromagnetic radiation like gamma rays, and gravitational wave detectors, which sense the wrinkles in space-time produced by distant cataclysms. The detection, which involved thousands of researchers working at more than 70 laboratories and telescopes on every continent, heralds a new era in space research known as multi-messenger astrophysics. This is the breakthrough scientists have been waiting for since the initial detection of gravitational waves 2 years ago. Now, for the first time, they are able to observe the universe using two fundamental forces, light and gravity. By combining traditional visual astronomy with the Nobel Prize-winning work of gravitational wave researchers, astronomers have new means to probe some of their field's most enduring mysteries: the unknown force that drives the accelerating growth of the universe, the invisible matter that holds galaxies together, and the origins of Earth's most precious elements, including silver and gold. "It's transformational," said Julie McHenry, an astrophysicist at NASA's Goddard Space Flight Center in Greenbelt, MD, who was involved in the effort. The era of gravitational wave astrophysics had dawned, but now it's come of age. We're able to combine dramatically different ways of viewing the universe, and I think our level of understanding is going to leap forward as a result. The existence of gravitational waves was first theorized by Albert Einstein a century ago. But scientists had never sensed the waves until 2015, when a ripple produced by the merger of two distant black holes was picked up by two facilities of the Laser Interferometer Gravitational Wave Observatory LIGO in Louisiana and Washington State. Since then, the collaboration has identified 3 more black hole collisions and has brought on a third gravitational wave detector near Pisa, Italy, to better pinpoint the sources of these minute distortions in spacetime. Just this month, members of the LIGO team were awarded the Nobel Prize in Physics for their achievement. Yet because black holes emit no light or heat, past gravitational wave detections could not be paired with observations by conventional telescopes, which collect signals from what's known as the electromagnetic spectrum. The scientists at LIGO and its European counterpart, Virgo, hope to detect gravitational waves from a visible event, such as a binary star merger or a kilonova. Kilonovas are swift, brilliant explosions that occur during the merger of neutron stars, which are ultra-dense remnants of collapsed stars that are composed almost entirely of neutrons, or uncharged particles. Collisions between neutron stars are thought to be 1,000 times as bright as a typical nova, and they are the universe's primary source of such elements as silver, platinum and gold. But much like gravitational waves, kilonovas have long been strictly theoretical. No scientist had ever seen one, until this summer. At 8:41 a.m. Eastern Time on August 17, a gravitational wave hit the Virgo detector in Italy and, 22 milliseconds later, set off the LIGO detector in Livingston, La. 3 milliseconds after that, the distortion rippled through Hanford, Wash. LIGO detects black hole mergers as quick chirps that last a fraction of a second. This signal lasted for 100 seconds, and it vibrated at higher frequencies. From the smaller amplitude of the signal, the researchers could tell this event involved less mass than the previously observed black hole collisions. "When we detected this event, my feeling was, wow, we have hit the mother lode," said Laura Cadinati, an astrophysicist at the Georgia Institute of Technology and LIGO representative. Just 1.7 seconds after the initial gravitational wave detection, NASA's Fermi Space Telescope registered a brief flash of gamma radiation coming from the constellation Hydra. Half an hour later, McHenry, the telescope's project scientist, got an email from a colleague with the subject line, "Wake up." It said, "This gamma-ray burst has an interesting friend. Buckle up," McHenry recalled. Gamma-ray bursts are the most energetic forms of light in the cosmos. Scientists had long predicted that a short burst would be associated with a neutron-star merger. That violent collision shoots jets of radioactive matter into space, as though someone had smashed their palm on a tube of toothpaste with holes at both ends. "We were beside ourselves," McHenry said. A map of all the observatories involved in the detection. Yellow dots are gravitational wave detectors, blue are for conventional telescopes. Caltech. Meanwhile, trigger alerts had gone out to LIGO collaborators at dozens of observatories around the globe. LIGO gave astronomers a narrow map of the sky to hunt for the source of the cosmic violence. It was critical to know where to look, said Ed Oberger of Harvard University's Center for Astrophysics. If we were just searching blindly across the whole sky, I don't think we would have seen it. Astrophysicist Marcel Sorre-Santos, a staff scientist at the Fermi National Accelerator Laboratory, compared the effort to seeking a needle in a haystack, with the added complication that the needle is fading away and the haystack is moving, she said, noting that light from kilonovas vanishes quickly, and the universe is in constant motion. At Penn State University, phones began buzzing during a science operations team meeting for NASA's Swift satellite. The 9:15 a.m. alert threw everything they had planned out the window, said Jamie Kenneyer, a Penn State astronomy professor. From low Earth orbit, the Swift satellite cycled through 750 points in the sky until it detected a vast avalanche of data in the form of ultraviolet rays coming from the neutron star merger. They were just in time. The UV emission disappeared in less than 24 hours. Ryan Foley, an astronomer at the University of California at Santa Cruz who studies supernovas with the Carnegie Institution's SWAP-A telescope, was walking around an amusement park when he got the urgent text from one of his collaborators. He abandoned his partner in front of the carousel, jumped on a bike and pedaled back to his office. He and his colleagues were up all night, first waiting for the sun to set on the SWAP-A telescope in Chile, then sorting through the telescope's images in search of a transient, an object in the sky that hadn't been there before. In the ninth image, postdoctoral researcher Charlie Kilpatrick saw it, a tiny new dot beside a galaxy known as NGC 4993, 130 million light-years away. He notified the group through the messaging service Slack. At Foley found something sending you a screenshot. Foley marveled at Kilpatrick's measured tone in those messages. Charlie is the first person, as far as we know, the first human to have ever seen optical photons from a gravitational wave event, he said. The event was named for the telescope that found its SWAP-A supernova Survey 2017A. The images used by UC Santa Cruz postdoctoral researcher Charlie Kilpatrick to identify the source of the gravitational waves. The image on the left, taken by the Hubble telescope, shows galaxy NGC 4993 in April. The image on right depicts the same galaxy on August 17. The dot in the upper left of the galaxy is the site of the neutron star collision. SWAP-A supernova survey via UC Santa Cruz. Within 24 hours of the initial detection, it seemed as though half the telescopes in the world, and several more in space, were tilted toward SSS 17A, recalled Stefano Valenti, an astrophysicist at the University of California at Davis who took part in the optical search. We were calling colleagues to talk, saying, "I cannot tell you why, but can you observe this object?" he said. Everyone was working together, sharing everything they had as soon the information was coming online. I think this one was the most exciting week of my career. The neutron stars merger was not a well-kept secret. On August 19, University of California at Santa Barbara astronomer Andy Howell tweeted, "Tonight is one of those nights where watching the astronomical observations roll in is better than any story any human has ever told." He told The Washington Post on Friday that part of him regretted sending the tweet, after observers and the media connected his and other astronomers' public hints to an event that set the world's observatories buzzing. Members of the collaboration still had 2 months of painstaking work ahead of them, confirming and analyzing their data to make it ready for publication. But Howell said he was motivated to mark the moment in scientific history. "I wanted to document what it felt like to find something completely new about the universe, that humans have never known," Howell said. The galaxy NGC 4993, about 130 million light-years from Earth. The kilonova is above and slightly to the left center of the galaxy. The MUSE instrument allows the emission from glowing gas to be seen, which appears in red here and reveals a surprising spiral structure. ESOJ, D. Lyman, age 11, NR Tama researchers collected data from the kilonova in every part of the electromagnetic spectrum. In the early hours the explosion appeared blue and featureless, the light signature of a very young, very hot new celestial body. But unlike supernovas, which can linger in the sky for months, the explosion turned red and faded. By separating light from the collision into its component parts, scientists could distinguish the characteristic signals of heavy elements like silver and gold coalescing in the cooling cloud of material. Wedding rings and uranium bombs are elemental echoes of these merging neutron stars. The observations confirmed theoretical models of what a kilonova might look like. For millennia, the two dead stars circled each other at nearly the speed of light, shaking off gravitational waves, which in turn pulled them closer together. When the husks smashed together, dinosaurs still walked the planet. The beams of light and gravitational shock waves from stars' collision finally reached Earth in August. The fact that the signals arrived so close together, just 1.7 seconds elapsed between the first gravitational wave detection and the arrival of the gamma-ray burst, also proves one of Einstein's predictions: gravitational waves move at light speed. While I'm not surprised that Einstein is right, McHenry said, it's always nice to see him pass another test. Scientists don't yet know what happened in the wake of the kilonova. Neutron stars are too faint to be seen from so far away, so researchers can't tell if the merger produced one large neutron star, or if the bodies collapsed to form a black hole, which emits no light at all. But after 2 months of analysis, the collaborators were ready to inform the world about what they have so far. Their results were announced Monday in more than a dozen papers in the journals Nature, Science and the Astrophysical journal Letters. The collaboration's capstone paper in Astrophysical journal Letters lists roughly 3,500 authors, approaching the record set in 2015 by 5,154 Large Hadron Collider physicists who estimated the mass of the Higgs boson. If gravitational wave research had already weakened the stereotype of a lone astronomer genius, the dawn of multi-messenger astrophysics dealt it a fatal blow. From this point onward, Cadonati said, the more we want to know, the more we need to work together. This kilonova was so bright that it could have been observed even by amateurs with tiny telescopes. In the future, LIGO will alert the whole world to potential detectors, allowing citizen scientists to join professional astronomers in the global search for light from the universe's most dramatic cataclysms. Francesc Cordova, director of the National Science Foundation, which funds LIGO, compared traditional, visual astronomy to a silent film. The earliest gravitational wave detections added sound, but they were little more than strange noises echoing in the dark, she said. We couldn't pinpoint the location of the source. Now, for the first time, the soundtrack of the cosmos has synced up with what scientists can see. It's all the difference in the world, she said. Saur Santos, a member of the Dark Energy Survey, said that multi-messenger astrophysics promises to help solve major questions in cosmology. For years, scientists have puzzled over what's known as the Hubble constant, a number that describes the accelerating expansion of the universe. Depending on how they calculate it, researchers get different values for this constant. Even just a dozen measurements based on gravitational waves, Saur Santos said, could dramatically reduce the uncertainties in those calculations and give a much better understanding of how quickly everything in the universe is racing away from us. This new era for astronomy may also illuminate the natures of dark energy, the mysterious force that drives the universe's expansion, and dark matter, a hypothetical substance that has mass and therefore should produce gravitational waves but seems to emit no electromagnetic energy. These two forces are thought to make up more than 95% of the mass and energy in the universe, and current physics can't explain them. We have so much to learn, Saur Santos said. This is an exciting time. And it's only just begun. Read more. Scientists detect gravitational waves from black holes colliding 3 billion light-years from Earth. Gravitational wave from black hole collision 1.8 billion light-years away sensed in US and Italy a year later. Scientists keep listening to gravitational waves, the soundtrack of the cosmos.